Well, I put it back in, so I don't know.
Yeah.
I'm scrubbing it.
You're different. No, I feel like it's like. Why should I do it? Maybe we should start carrying like baby wipes or like alcohol wipes or anything. Yes.
Okay.
Hello. I'm Nashira. Welcome to this presentation. So during the literature review process of my research, I have come across this very interesting approach
Are
to...
you not on the screen online anymore? I can't see it anymore. Stop sharing, sorry.
The screen or the sound?
No, the screen, the presentation.
Okay.
Yeah, if you go in and out, you have to
It's only when
reshare.
I join and then it stopped. Oh, I think it's back. Yeah, it's back. Thank you.
Okay. They have researched the constitutive methods, which are a very interesting way of designing the network architecture. And I would like to talk about these and how they differ from the popular physics-informed neural networks. So both constitutive methods and physics-informed neural networks are approaches to introducing physical knowledge into a neural network model. And the motivation in my project to using one of these methods is that I am wanting to model the deformation of the cortex. And this is a process that can be quantified by physics, and there are plenty of mathematical models that try to describe this. So instead of simply using a general network that would learn from from the data that it sees, we can also introduce some physical concepts to the network with one of these aforementioned methods. And currently we're using only a pin. The mechanical response of the brain cortex when it undergoes deformation is characteristic of a hyperelastic material. So we can use the hyperelastic models. And a very commonly used example of a hyperelastic model for brain modeling is a Neo-Hookean model. This equation calculates the strain energy density W from the deformation, where the deformation comes into the variables I1 and J. And minimizing this equation would be equivalent to finding the configuration of the material where it is at a mechanical equilibrium. The physics-informed neural network would integrate this physical knowledge into the model by optimizing the physical concept. Therefore, the pin would minimize the strain energy density of a deforming hyperelastic material. And therefore, this would mean to encourage the model to produce physically plausible solutions according to what the Neo-Hookean model can describe. However, the neural network block itself is flexible with its outputs, so it is technically free to violate any of these physical constraints. It would be the physics laws a posteriori of the result of the network that would be minimizing the violations according to the Neo-Hookean model. So even when using the Neo-Hookean model, if it's with a pin, the Neo-Hookean model wouldn't be imposed on the outputs. Really, it's just the network that's being encouraged to minimize these violations. So technically, the model would be free to violate these physical laws, again, when extrapolating to thin examples. The idea behind the constitutive methods is that the network would automatically satisfy the physical requirements, only producing physically reasonable outputs. This can be implemented by explicitly modifying the network input-output architecture, therefore hardwiring the physics into the network design. A really dummy example would be that if you know that your output image needs to only be made up of positive numbers, you could analyze the negative outputs using the loss function, or instead you could modify the network architecture by adding an activation function that only outputs positive values. And then the loss function doesn't need to deal with the negative values and can be focusing on something else. In the context of hyperelasticity, there have been constitutive models built to satisfy the requirements of hyperelastic materials. And since they are neural networks, they still have some of the flexibility of being a data-driven method. One of these constitutive models for hyperelasticity is the CAN, Constitutive Artificial Neural Network. And the idea behind the CAN is that it would reverse engineer the input of the network to account for material objectivity, symmetry, and incompressibility, the network output to enforce thermodynamic consistency, the activation functions to implement other physical constraints, and the network architecture to ensure polyconvexity. We can see what this means by looking at the construction of the CAN architecture. So firstly, the CAN considers that in solid mechanics, the constitutive equation defines the relationship between a stress measure and a deformation measure. Here we can use the PL of stress P and the gradient deformation tensor F. And so the first step in this method is to ensure thermodynamic consistency. And this implies that the stress of a hyperelastic material is a thermodynamically conjugate function of the deformation gradient. Therefore, the network can ensure thermodynamic consistency by learning the free energy function as its output from the deformation tensor F and calculate the stress in a post-processing step. The second step is to ensure material objectivity. The material objectivity implies that the stress response is independent of rotations and must be functions of the right Cauchy green deformation tensor C. Therefore, rather than using the components of the F tensor as inputs, the neural network will have the components of the symmetric right Cauchy deformation tensor in its inputs. Next, they ensure material symmetry for the spatial case of isotropy. This requires that the energy function of the left and right Cauchy tensors would be the same, and that the stress response would be functions of the invariant of the left and right Cauchy deformation tensors. Therefore, the free energy function is decomposed into the terms of the three invariants, and these would now be the inputs to the network. For the particular case of incompressibility, the Jacobian matrix, which is the third invariant of the Cauchy deformation tensor, remains 1. Then the free energy function that can be simplified to depend only on the first and second invariants. For the neural network, if dealing with incompressible materials, this means that the inputs need only be the first and second invariants. Further reasonable constraints would include a stress-free configuration. This can be introduced to the network by, instead of using the invariants themselves as the inputs, using the deviation from the stress-free reference configuration. Additionally, the free energy is non-negative for all deformation states, 0 in the reference configuration, and infinite at extreme cases of infinite compression and infinite expansion. These conditions can be implemented through the choice of activation function, using only monotonic, continuous, unbounded, and 0 at the origin activations. While the general definition of the free energy function would be made up of the product of powers of invariants, the mixed products of the independent invariants generally produce non-convex functions. Therefore, if we wanted to ensure polyconvexity, we should use a subclass of free energy functions, which would be subfunctions derived from each of the invariants and would only be combined additively. Therefore, to introduce polyconvexity into the network, we would decouple the invariant inputs, not connecting the neurons of each invariant, such that they are only combined additively in the last hidden layer to output the total free energy function. Putting all of this together yields the resulting network architecture. Firstly, the inputs gets decomposed into the invariants, which are functions of the Cauchy deformation tensor and deviated from their stress-free reference configuration. We can note that this diagram can be simplified if we were to use only the first 2 or 3 invariants, depending on the material we were using. The connectivity of the network has been modified to decouple the invariants to satisfy polyconvexity. The activation functions F1, 2, and 3 in the last layer would only be thermodynamically admissible ones. And the output is the free energy function, which would be a function of the original deformation gradient tensor, from which the stress would be calculated in a post-processing step, therefore satisfying thermodynamic consistency. There will be several advantages and disadvantages of choosing this kind of architecture, which would of course depend on the application. For example, when implementing a physical concept through a constitutive model, the concept is enforced, not simply encouraged. And this will be an advantage in the case of limited data or when we are very confident in the concept, such as when applying a constitutive law. However, it will be a disadvantage if, for example, you wanted to simply encourage some model which may not fully represent reality to help the model, but really let the network learn directly from the data. Also, this particular CAN is a fully connected network, which would be a disadvantage if dealing with spatially dependent data, because it wouldn't be taking advantage of convolutional networks. And in the context of my project, the model which is currently outputting the deformation field from a CNN could complete the constitutive relationship by using a second network with a CAN architecture. And this would receive the output from the first network and find the stress field for the corresponding strain. And unlike a general network, by using a CAN to predict the stress, it would automatically be thermodynamically plausible. And this thermodynamic consistency should backpropagate into the first network as a regularizer for the deformation field. Thank you.
So go all the way back to no, next slide. Okay. Keep going. So the first law we're familiar with, which is that we have this constitutive relationship between stress and strain. Okay, next slide. Keep going. Okay. Material objectivity. The stress response is independent of rotations. That must be a function of the right Cauchy green deformation close. Why? Is that what enforces the rotational invariance?
I believe the thing is that this is the one with the no. I think so. That's what the paper said.
What did you?
I said that material objectivity implies that the stress response is independent of rotations and must be functions of the right Cauchy green deformation tensor. So I believe by using the Cauchy deformation tensor, which is a function of f, this would mathematically imply that there's objectivity.
It must be what I can't figure it out right now. It must be what enforces this rotational invariance.
Decomposing the like using the c, which is a function of f.
Because like one must follow the other, right? If c is just a function of f, then you're not doing anything by just changing the function unless that is what enforces the invariance.
It looks like it.
So what's the f again?
The deformation tensor.
The output that you get from the CNN.
Yes, if we were to use it like that.
Yeah, okay.
So I understand that.
Because that's like if you, for rotation matrices, the matrix times its transverse. It's like the transverse is the invariant, is because they're, you know, like in PCA, like if it's a rotation, then a rotation matrix, the inverse of a rotation matrix is equal to its transpose. So then that the C should be the identity matrix for rotation. Something like that. Something to do with that. Okay, next one. Material isotropy, special case of symmetry, implies that the stress response function must be functions of the
left.
So that's just
information
following
tensor.
on from the previous, right? So
Yes.
material isotropy, so invariance to rotations implies that the stress response has to be a function of this Gaussian deformation tensor.
Yeah, but there's the left and right, and they have to be equal if you want to have symmetry.
What's B?
Sorry?
What is B?
B is the left Cauchy deformation tensor, so instead of multiplying the transpose on the right, you multiply on the left and you'd get B.
It has invariance of C and B. Oh, so now we get I1, I2, and I3.
The invariants are part of what describes the Cauchy deformation tensor, so it's still the function is still a function of C, but you've decomposed it to be functions of the three invariants, which are functions of C.
Yeah, can you go back to your original definition of strains on like
It's one.
right at the beginning? Before that. Strain energy. Yeah. So they will plug into this equation. But here we only have I1.
Yes.
Joe's the Jacobian, isn't it?
Yes.
Do you have somewhere like W written out in terms of I1, I2, and I3?
That wouldn't be the Neo-Hawkian model. That wouldn't be the Neo-Hawkian model, it would be another model.
So then you only need I1.
If you're using Neo-Hawkian models, yes, but the constitutive architecture is like a generalization of all of the models. So by choosing to use more or less invariants, you could be constructing the other models that are used for.
Sounds straightforward enough then.
In this case, what are the constraints that you show data that you are implying with this loss?
This is a much more constrained model because this is an actual mathematical model that someone probably called Hook figured out.
That's not right.
Yeah.
Yeah.
But the concepts I was describing afterwards were real concepts of very established concepts of thermodynamics.
Okay.
But this is a very specific case, which may or may not fully describe the real behavior.
We're only gonna ever want to do right? So these are like generic, these constitutive. Is this any type of
This
constitutive
architecture here.
artificial networks for various different
Yes,
elastic deformation type models?
yes. With this diagram, we could figure out all of the others because it just this puts in the thermodynamic concepts all together. But can you see how there's like 4 inputs coming out of the F?
And we just need one.
We just need the first one if we're using the Neo-Hawkian model.
Yeah.
If you use 2, that's another model. 3, that's another model.
Take that way, in fact.
Yeah, I think so.
What are these though?
Those are powers. Because I believe that comes from the general way of representing the function, which can be powers of
What the JK now?
the JKA are material constants, but can you see how the first invariant, technically the deviation, is being multiplied with the other and the other, and there's powers to them.
That's JK now.
Yeah, so I imagine that's what it's doing, the first part. And then there's another layer with activation functions, so you can only use thermodynamically consistent ones.
You have examples?
Admissible.
That's like sigma in this respect.
I think one of the ones that they used was the exponential function.
If again the constraint for catch.
The activations need to be monotonic, continuous, unbounded, and 0 at the origin.
They tell you which activations they use.
I think it's the exponential, yes.
Because basically there is code for this in terms of code.
Yeah.
But if we only have to just implement it for like I1, then we can have a pump.
I think Mariana has a question.
Oh, no.
Mariana?
Hey, sorry, I'm a bit. I think my brain is kind of fried from this code, so it might be basic. I didn't really understand like what is actually being like trained in this like what are the actual parameters and like how the loss function actually works in like the cans. I'm a bit lost. Like so you input like the deformation.
Is it trained with like ground truth finite element stuff?
Yes, it's the loss is just an L2 loss with data that they have. So in this paper, they use supervised.
Oh, okay. Okay, I guess that's just everything I was not getting. Okay. So then like how would you use it like in the case? Like
In
for
the case that
example,
in like our model. you mean?
yeah.
So we have the neural network, which outputs a deformation field. You can decompose the deformation field into the invariance, deviated, the stress-free configuration, and that would be the input in the beginning.
But we only need I1. And so basically, instead of outputting the parameters of the deformation plus the 6 independent values of the stress tensor, you only have to output the deformation from which you estimate this using the physical law. So you're less likely to overfit because you don't have to estimate so much.
You mean using the CAN?
Yeah, because if all it is a fully connected, like a very simple network with very few connections.
Yeah.
And a few nodes, that's just basically enforcing what.
Like in the loss,
But what
if
is
we had
like what is the L in there, like that loss in that case?
this would be, well, we would have the deformation U from the first network, from which we can we can calculate the stress, but then we can also have the stress calculated from the CAN, and we would have to make this equal to each other, and that is another physics equation. So in our loss, we would make the P, which we calculated from this U that we predicted, and the P that we predicted with the CAN, we would make those equal and penalize the difference between those.
Okay. And why is it that more like why is it that better than to just like estimate?
That myself, right? Because what we're doing is like estimating you.
No, I mean like what is it like
manually calculate all of these different things in order to get P.
yeah, but like what is the difference between like using the CAN or like estimating like you were saying like the like instead of just estimating the U, like estimating like all the stress terms like directly from the CNN?
If you're forcing the physics through the CAN, this physics would be backpropagated into the first network, and that would be the advantage, that you are enforcing some kind of physics.
I mean, I'm still confused a bit by like these Baena papers and stuff where they're like, well, I mean, without that extra stress divergence term that they've got, just outputting some parameters for P, the stress, and forcing them to be equal to what you calculate from the deformation doesn't seem much of a constraint. So here, I guess it's constraining them a bit more, that the actual stress that you're calculating from F here is really forced to obey that equation.
Yeah.
Okay.
You'd have to benchmark and see whether it actually pragmatically made any real difference. It also doesn't sound like as difficult as it initially did.